Right now, beneath the floorboards and concrete of the buildings you walk past every day, a quiet standoff is happening. Every standing structure is in a permanent negotiation with gravity, fighting millions of pounds of downward force. When a foundation begins to rot, or a brick facade leans too far out, engineers have to step in. But fixing a building often means removing the very walls or footings that hold it up. The moment you cut away that support, gravity is no longer a passive force. It becomes an immediate threat. This triggers what engineers call the transfer moment. It's a temporary, highly volatile window of time where the massive weight of a structure must be perfectly caught, suspended, and moved to a new path before the old one is destroyed. To survive this window, crews rely on three distinct systems. Shoring handles the temporary support inside, underpinning manages the permanent rebuilding below ground, and scaffolding provides safe access on the outside. If these systems are deployed correctly, the building survives the transfer because it has been physically tricked. As far as the structure is concerned, nothing has changed. When a masonry wall starts buckling outward, it can no longer carry the floors above it safely. The weight pushing down needs an entirely new path to the ground, fast. This diagram illustrates one solution, the raking shore. It catches the falling wall by redirecting its weight diagonally away from the compromised brickwork. To grip the masonry safely, the shore uses specific hardware. A wall plate is placed flush against the brick. Then, a timber needle is driven straight into the wall to bite into the structure, while cleats lock the heavy diagonal raker beam into place, catching the downward force. Workers cut literal holes through the existing masonry and insert a thick, horizontal steel beam, also called a needle, straight through the wall. They then brace that needle with vertical props planted firmly on both sides. Once those props take the weight, crews can safely cut a massive opening out of the brickwork below. The entire upper half of the building remains suspended mid-air by the needles. Steel props and wooden needles can only hold a building for so long. Shoring is a stopgap. It buys the engineers the time they need to solve the real structural failure, which is usually buried in the dirt. Deep below street level, away from scaffolding and shoring, lies the decaying foundation. Fixing this requires working underneath a structure weighing thousands of tons. There is one cardinal rule when repairing a foundation. You never excavate the whole trench at once. Doing so guarantees an immediate collapse. Instead, the dirt is dug out in a strict checkerboard sequence. In this diagram, Bay 1 is excavated and filled with wet concrete, while Bay 2 is left entirely untouched. That untouched section of earth is carrying the entire load of the building directly above it. It holds the line for days while the new concrete in the adjacent pit hardens, cures, and eventually safely hands the weight off. This cross-section illustrates how tight the margins are down here. Before the dirt is even moved, structural needles and heavy-duty jacks are wedged in to brace the old foundation. Look closely at the wooden bearing plates inserted between the steel beams and the existing masonry. They distribute the massive point load of the jacks, preventing the historic brickwork from being crushed during the transfer. After weeks of this slow, methodical excavation, the building is standing on a massive concrete footing that did not exist when the project started, and the occupants inside never felt it happen. Back above ground, managing the static weight of brick and steel is only half the math. Engineers also have to account for dynamic, unpredictable forces, the heavy materials, the wind, and the human workers. That requires scaffolding. A scaffold is a highly calculated temporary twin of the building itself, erected purely to let humans safely walk in the sky. This schematic of a bricklayer scaffold breaks down the anatomy. The vertical standards carry the weight of the workers straight down to the soil, while the horizontal ledgers hold those uprights securely apart. But to stop the whole grid from peeling away in the wind, it must physically tie back into the building. Notice the transverse put logs on the right side of the diagram. They slot directly into the existing masonry, turning the building itself into an anchor. Every pole, base plate, and tie is mapped out to handle maximum soil pressure and live load. It is an entirely separate structural skeleton, constructed just so workers can occupy a space that technically isn't there. When you step back, the true scale of a major retrofit comes into view. Scaffolding wraps the exterior, shoring pops up the walls from the inside, and underpinning locks the foundation deep underground. These three systems are often installed by completely different crews, operating on separate schedules. Yet they must perfectly synchronize to create a rigid triangle of force that ensures the building remains perfectly still. Each individual system carries immense weight, but they are designed with a specific redundancy. They exist so that if one point is stressed, the others can safely absorb the shock. Every historic structure, every retrofitted skyscraper you have ever walked into has at some point been quietly and deliberately made unsafe, just long enough for a team of engineers to trick gravity and rebuild the structure stronger than it was before.